everyone. Today we are lucky to have the newly minted Associate Professor Vera visiting us from the University of Southern California. She's searching for new physics from near to far. Vera got her PhD from Caltech. At that point, we were working primarily on cosmic microwave background physics, and then through a postdoctoral fellowship at IAS and her time as faculty member, he has branched out tremendously, looking for astrophysical signatures of new physics across the cosmos. Her work on that has already been recognized by a Gabriel Professorship, an NSF Career Award, and a Quadrella Scholarship. And today we're lucky to get the tour. Please.
Thank you, Elizabeth. And thanks everybody for having me here and for sticking around on a hot afternoon. So I come from sunny LA, but maybe not as hot as here. And I'm here to give you really a sampling of some of the newest results from my group and related work that I'm really excited about. But before I start, and I'm going to be pacing a lot because I don't have a clicker, I have to give due credit to all the amazing junior students and postdocs who stand behind all the work that you're going to see in the next hour. So as I move through my slides, please take note of the highlights on individuals there. And of course, I have been told that this is mostly expert audience. It's more like a seminar, but I am going to indulge in an introduction that has some nice visuals. So stay with me on this. Of course, the story of the search for new physics with cosmology starts with a picture like this. And for centuries, we've been staring at the night skies with eyes and with telescopes and calling that astronomy and maybe cosmology, a discipline that's supposed to tell us what the universe as a whole is about. But now we realize that 95% of the budget of our universe is invisible to us. And in particular, we now know that everything that you've ever seen in the night sky or on Earth, or that you've studied in the physics courses, all of the matter that we interact with accounts for nearly 15% of all the matter in the universe. And if we had the eyes to see the rest, our sky would look more like this. Computer simulation that's matched to small and large Magellanic clouds in here, and this gravitational scaffolding that supports structures on nearly all visible scales is made mostly of dark matter. And then of course, all that space-time is in addition accelerating its expansion, which it shouldn't be doing if it was filled only with gravitating matter. So there is that pesky dark energy on top of it all. And dark matter and dark energy together constitute the main components of our universe today. But this pie chart didn't always look like that. And so if we rewind back in time, and again, indulging here in some Cosmology 101, pay attention to that little sliver, red sliver of radiation that, if we wait a moment, starts growing towards the beginning, towards the Big Bang, to the point that at the time when the light elements were synthesized in the early universe, for example, neutrinos, standard model neutrinos constituted a solid third of the energy budget in our universe. What I want you to remember from this heuristic story is that cosmology and then the microphysics of particles that constitute the main components of our universe are very tightly knit together, in part, in a sense, because our universe started in the quantum realm, if you wish, and expanded very fast and has been expanding since its birth. So when we look at the scales on this macroscopic universe and structures within it, those structures have a memory of those early times when particle physics mattered and it was able to change things around. And of course, there's a memory of all the epochs in between. So of course, the big goal here is we want to know the census of all the particles and all the forces of cosmological significance. But for the sake of time, I'm going to focus on two questions that have driven a lot of the work that I've been doing in recent years. And one question is understanding the fundamental nature of dark matter. The other question is understanding the fundamental nature of our standard model neutrino particles, which are arguably perhaps the most elusive bit of the standard model of particle physics. And of course, the observational context, as I know all of you are very familiar with, is that we have a small army of telescopes and surveys, ground-based and space-based, that are already delivering and will be delivering data over the coming decade. And that will open up very large space for new discoveries in many different directions. But I will say, I work with a couple of these observational collaborations, but I'm not representing any of them in this talk. So instead, what I want to do is I want to focus on the story of what we can do with fundamental physics when we leverage different probes together. And when I talk about cosmological observations, for a cosmologist, I'm going to focus on one particular quantity, and that would be the distribution of matter as captured by a variety of visible tracers from the CMB and isotropes all the way to dwarf galaxies in the local universe. And as quantified by this particular quantity called the linear matter power spectrum, which gives us basically an idea of the amount of structure on a particular physical scale that's shown on the horizontal axis here. So when you see plots like this for the rest of my talk, and when you look at high wave numbers, I want you to think small scales, and I want you to immediately think these are the seeds of structure that will one day grow to become dwarf galaxies in the present day universe. And when you look on the left-hand side of plots like this, I want you to think seeds of large scale structures. So galaxy clustering, CMB, all the stuff that we capture in these kinds of surveys. So for the rest of the talk, I really want to break down things in terms of the variety of scales and talk about what we learned from different scales about different bits of potential new physics. And I'm going to start by talking about the microphysics of dark matter particles and review some of the results, some of the new findings that we made by looking at structure within the Milky Way. So structure on galactic and subgalactic scales as the first part. But I can't really go into this without giving just a tiny bit of theoretical background. So we do know a lot of general things about dark matter. We've known them for a while now. For example, the cosmological abundance. For example, the fact that dark matter cannot possibly interact very strongly with anything in the standard model. So it's not one of the standard model particles. Moreover, we have evidence for it from a variety of observational probes. And we know that dark matter has been around since, since the Big Bang pretty much. And over the past few decades, a lot of the experimental effort to find dark matter particles has focused on one particular well-motivated paradigm, which is the weakly interacting massive particle, or the WIMP. And since these direct detection experiments, some of the results are summarized here in terms of exclusion curves, have not yet seen a signal, a lot of the theoretical effort proliferated in terms of designing new theories, which can explain the absence of signals in direct detection and offer new ideas for paradigms for what dark matter may be. And many of those are summarized in this diagram on the left. I don't ask you to read any of the words on that diagram. I'm simply trying to communicate that there's lots of them. I will mention a couple of these candidates, but the bottom line is we do have a lot of ideas. However, if you're a cosmologist like me, what you really cosmologically care about is not going to be so much a detailed description of what dark matter is doing at high energies. So you're not going to be so much interested in a high energy Lagrangian describing dark matter particles, but what you do care about is what dark matter is doing effectively at low energies. So how it's interacting with the standard model particles, with itself, how it's produced, and also what are the masses involved of the particles that we have. So in a sense, in cosmology, we can afford to adopt this very broad brush scan for dark matter and hunt for its basic characteristics. And broadly, very, very broadly speaking, dark matter microphysics can mess with the universe through several different processes. For example, it can be born with appreciable free streaming velocity. And so in that case, we call it warm dark matter. And warm dark matter can stream out of gravitational potential wells, and with that suppress structure on small scales. It can also interact for example, with baryons. And if it does so, it may seep heat out of gas at various points in cosmic history and affect perhaps star formation or other things about the objects, about visible objects in our universe. It could annihilate and dump entropy into radiation and therefore cause a change in the expansion rate in the early universe. It can also be a bosonic particle with appreciable galactic size, de Broglie wavelength, and change the interior structure of galaxies. But all of these processes also come with appropriate alteration in the linear matter-power spectrum. So I'm coming back to that quantity here. And in a way that's captured with this summary plot that's made for the SNOMAS report. So what's shown here, the cold dark matter, uninteresting, non-interacting beyond gravitational interactions, dark matter is shown with this gray line. And then all the colored curves correspond to different paradigms that I mentioned on the previous slide. And what I want you to take from this plot is, one, most of the data points are on the far left on large scales, because those are the scales that are easier to probe and to model. But most of the differences between all these different paradigms show up on small scales. So small scales, in a sense, are kind of a gold mine for searches for dark matter microphysics. However, if you want to model small scales, you run into this heartbreaking issue that you have to leave linear cosmology and linear perturbation theory behind and model systems that are highly nonlinear, maybe go to running cosmological simulations. And things like this are very difficult and computationally expensive to do, as many of you know. And so they have been done in detail only for a subset of these paradigms. One of the ones that was explored in detail was warm dark matter, for example, and a few others. But I want to focus on a totally different paradigm here, one in which dark matter interacts with standard model particles, baryons. And so, for example, imagine elastic scattering between dark matter and protons. If you allow for dark matter to scatter with protons very weakly, what you end up doing is you end up putting into thermal contact dark matter and baryonic fluids at some point in cosmic history. And this leads to both momentum transfer and heat transfer between the two fluids. And depending on what this momentum transfer looks like as a function of redshift, I'm only putting this equation there because I've told that you guys are fans of Boltzmann equations. So I totally expect that you all know exactly what it says. That's a joke. I'm putting it there because some people think in equations, some people think in pictures, and so I like to be complete, all right? So depending on what your momentum transfer rate really looks like, which is driven by the nature of the interaction at hand, you will end up doing different things to the distribution of matter throughout cosmic history. But one common thing that ends up happening is that you suppress power on small scales. So let me illustrate what I mean by that. So if you simulate a halo, a dark matter halo like the Milky Way, and you do that in cold dark matter cosmology with no interactions, you will notice, and this is dark matter only simulation, you will notice a lot of substructure on small scales. In these subhalos, many of them end up hosting small galaxies, which we know exist and orbit around the Milky Way. But if you turn on a small amount of interactions with protons, you couple that dark matter to protons, and through that you couple it to radiation, you heat it up, and you cause collisional damping of small scales. So some of those subhalos that formed in cold dark matter cosmology never formed in interacting dark matter cosmology, and so the galaxies that they would host are no longer there. In terms of the linear matter power spectrum, this translates into erasure of structure on sufficiently small scales. In particular, on scales that are smaller than the mean free path of dark matter particles, free streaming lines of dark matter particles. And so this quantity here, I'm not sure how much people are used to looking at it, is another version of my power spectrum, which I love, because here I've normalized the P of K matter power spectrum from cosmology with interactions to that of CDM. So I can only look at comparisons here. So when the blue dips, so CDM is the black horizontal line. So when the blue dips below the black, that means suppression with respect to CDM. Okay, so on large scale, structure is intact. On small scale, structure is suppressed or even erased. Now, the one free parameter that matters the most in a cosmology with interactions is the interaction cross-section. And so you can move this cutoff towards smaller physical scales. So in other words, towards the right here in this diagram, if you reduce the strength of the interaction. Okay, so what you do in that case is reducing the strength of interaction makes this interaction decouple earlier on in cosmic history. And so it affects only the scales that were able to enter cosmological horizon prior to decoupling. Okay, the scales that enter after decoupling are intact. All right, so now next thing we want to understand is we can translate this linear matter power spectrum into the abundance of dark matter halos in present-day universe by running cosmological simulations. But I want to deal in linear theory for the moment. I don't yet want to go into simulations. So what I'm going to do here is I'm going to relate the scales in the wave number k in inverse megaparsecs moving to roughly the masses of halos that form roughly from those scales. Okay, so something like 30 corresponds to a few times 10 to the 8th solar mass subhalo. Okay, scales intertwine in nonlinear cosmology, so this is not an exact mapping, but order of magnitude it works out. All right, so now from surveys like SDSS and DS and PanSTARRS and soon LSST and so forth, we are actually able to find small galaxies in the orbit around the Milky Way. So in other words, we are able to make a census of satellite galaxies of our own Milky Way. And when we account for observational bias, the fact that these are faint systems, they're hard to see. If they're faint enough, we're not going to be able to number all of them, but we can infer the presence of other ones that we haven't seen. And then also just understanding the observational biases of the instrument itself. The census of Milky Way satellites today from these observations implies that there are subhalos down to a few times 10 to the 8th solar mass. So in other words, we've seen galaxies whose existence implies that dark matter has structure on those mass scales. Okay? Now, in linear theory, I've made a point to say that that corresponds to wave numbers of about 30 inverse megaparsecs. So the game that I can play now, if I want to stick with linear theory, I can say, okay, so let me figure out how strong do I need to make those interactions with protons to completely erase halos that are of that mass, to erase any seeds of structure on those scales. So in other words, let me move this curve such that it hits 0 right at 30. Okay? Suppression, but completely destroy the seeds of structures on the scales, no structure exists. And so by playing this game and then turning it into full likelihood analysis of the population of satellites, we get very similar answers with two different data sets where the red line corresponds to a slightly better, slightly more complete census of satellites. We were able to exclude cross-sections for each individual dark matter mass that are above the red line in this diagram. So everything shaded is excluded by the existence of substructure within the Milky Way. Okay, so two take-homes here, or maybe three. One is that even doing such a, I would say, robust approach of not bothering to model the population of satellites in a modified cosmology in great detail, but simply say what we can say with great certainty, we are able to push beyond linear theory, beyond the CMB bounds on the very same physics by several orders of magnitude. Second point is that we are starting to graze the top of the exclusion regions for the same parameter space in WIMP searches for dark matter. So we're starting to close the gap between direct detection and cosmological searches. And then the third point is that we can push to really small dark matter masses that are borderline of being 1. So 10 keV, between 10 keV and GeV scale. All right, now one little bit that I haven't told you about here is that this whole analysis relies on the assumption that the interactions are velocity independent. However, you can ask the same question: what do you need to do if you want to have velocity dependent scattering? For example, interaction cross sections that are parallels of relative particle velocity. And these kinds of interactions cover a good range of possible effective theory operators for dark matter proton elastic scattering. So in other words, it covers the possibilities of effective theories for what these interactions could possibly look like at low energies. And you can play the same game and ask, how much do I need to tune up these cross sections in order to erase all the satellites from the Milky Way? And yet again, you get exclusion. So N here denotes the power law index. For different interaction types, you again push this blue a few orders of magnitude below linear cosmology. I'll conclude this bit of the story by just saying that in comparison to the CMB, where we were probing these interactions at times that are maybe right before recombination after redshift of something like 10 to the 4, when we start asking questions about structure formation that leads to satellite galaxies, we're effectively probing interactions that decouple when the universe was about a month old. All right, so I want to change gears completely here and talk about sterile neutrinos. So I'll pause for a second and see if people have questions. I've talked to half of this room already about all of this stuff. So I'm sorry, guys, you're hearing this stuff the second time.
Is there an interaction cross section below which you would say there is no interaction?
There's no interaction. So is there a benchmark that we can go for?
Yeah.
Not to my knowledge. You can cook up specific high energy models where this might be the case. But what we're going after here, we can constrain these models because we can. We already have the data. But it's very hard to design a particular benchmark with the walls. So these are not twins. These are much lighter particles that interact in it through different mechanisms. Yeah.
Someone stop screen sharing.
Oh.
And please do share through Zoom.
Miracle just happening. Are people okay with this partial coverage, or should I don't know what just happened. Now I can see the notes, but I can't see that.
I really hope we just go back to purely in person at some point. That will also increase the audience.
For people.
Just do whatever is convenient.
I would love to. Turning my back to everybody else.
I'm not sure, but that just goes.
Wait, hold on, I got it. I regret that decision. Okay, all right, I think I had another question.
Oh, yeah, thanks. So I'm just curious, I'm mainly interested in sort of planet formation and dynamics. I think it's intriguing that the knowledge of these, small halos purely comes from like essentially one system, right? The Milky Way.
Oh, we do.
That I guess is subject to, well, okay, maybe you're going to tell me it's more. I just saw these Milky Way curves. But I guess I teach in my class that all these satellites are subject to dynamical friction and lots of other messy things that happen. So how well do we know from what we currently see, and tracing that back to cosmology.
Yeah, so there's, thank you for the question. We do have a census of substructure in the local group. It goes broader than the Milky Way, but this is where we're most complete. This is where most of the reliable knowledge comes from. But you're absolutely right. There's a lot of basic physics that goes into the dynamics of small helios within the Milky Way. So I wanted to lead you to order of magnitude theorists' guesstimate of where this bound would be. Model, for example, the halo stripping within the Milky Way potential and the baryonic effect, to the best of our knowledge and so forth. You can marginalize over the galaxy halo connection models and all the parameters that describe all this messy physics, and you end up with a bound that's within a factor of 2 of my analytic estimate. So the robustness of this answer comes from the fact that I'm not actually trying to design a method that can claim discovery. What I'm doing is I'm leveraging extreme case scenario, right, where I simply have no structure to begin with on corresponding scales, and then asking a question, what does that mean to the interaction strength, right? But if I want to turn this method into a discovery method, then I need to worry very much about how I model in detail. And this was done in a handful of cosmologies, particular for Warnberg. Okay, I'm going to move on, and now I want to talk about a little bit sneakier paradigm that doesn't talk to the standard model by coupling to baryons, but actually talks to the standard model by only coupling to neutrinos, which are anyways very difficult to measure. So this is a very convenient model to hide dark matter that does have interactions, but doesn't mess with cosmology, or so the hope is, very much. So sterile neutrinos are this idea that has a lot of theoretical motivations behind it, one of which comes from an attempt to motivate the existence of the mass of standard model neutrinos, which requires some beyond standard model physics and so forth. But for cosmologists, this is the story. So Donaldson and Widrow in the 90s came up with this idea, okay, so neutrinos are very elusive, so maybe we can make dark matter out of neutrinos. But we would need to make this fourth neutrino somewhat hidden from the standard model and can have weak interactions. It needs to be sterile and not charged under any standard model forces. And let's make it heavy, so KV mass scale, so it's not too warm. And let's make it mass mix with active neutrinos. So do the same thing that the 3 that we know of do. So assign some probability of conversion of an active neutrino of whichever flavor to the sterile neutrino that's captured by the mixing angle of theta in much the same way as the mass mixing happens within the standard model. So this kind of a particle would be produced non-thermally in the standard model. What does that mean? It means that it would never interact sufficiently with the standard model particles in the early universe to thermalize. So it would be produced only through this mixing occurrences. So while the standard model neutrino is undergoing all of these standard model interactions in the very early universe, it decouples at about an MeV temperature. But while it's coupled, there's some probability of converting a portion of those active neutrinos into sterile. So the abundance of sterile neutrinos slowly builds in proportion to this mixing angle, while the active neutrino is thermally coupled to the rest of the plasma. Once the decoupling happens, the abundance freezes out, and we have hopefully all of our dark matter made out of these particular particles. However, if you want a fourth neutrino mixing with active neutrinos, one of the processes that has to happen given a large enough mixing angle is the decay of these neutrinos and a production of X-rays in regions of our universe where there's a large concentration of dark matter. So in other words, galaxies and halos. Since we haven't seen galaxies in our neighborhood glowing weirdly in X-rays in excess, that puts a bound on how much mixing there could possibly be as a function of dark matter mass. Now the problem is, if you want to produce all of dark matter in this manner, it also gives you a specific locus in this parameter space where you have to live, this black line. For any given dark matter mass, you have to have enough mixing to be produced in sufficient amount. So unfortunately, this original Dodelson-Widrow mechanism is completely ruled out by X-ray observations. However, this kind of mechanism of producing dark matter is so appealing that people have devised ways to work around this particular bound. And one very simple way that comes from Vera and company that kind of captures what happens in other such scenarios as well, is one in which they invoked another unknown new interaction between active neutrinos that's mediated by a heavy mediator phi, new particle, probably a heavy scalar, with a coupling strength lambda in this case. And if you introduce these interactions, you basically produce another channel for production of sterile neutrinos. In other words, at a fixed mixing angle, you can boost the production of steriles in the early universe through these two different Feynman diagrams. So this is essentially an expansion of the parameter space that adds the mass of the mediator and the coupling constant as two other free parameters in the model. So that opens up the region of the parameter space in terms of the mixing angle where you can live between these two red regions and still produce cosmological abundance of dark matter. So it's no longer a line, it's a whole region in the parameter space. Okay, however, if you produce sterile neutrinos through mixing with active neutrinos, you're kind of committing yourself to indirectly talking to the standard model while the universe was very hot. So even though these particles are not thermalized, maybe they don't have thermal velocity distributions, their phase space distributions can be calculated depending on the particular production channel. And what ends up happening is that you produce a cosmology where dark matter, the sterile neutrinos, actually do free stream quite a lot, depending on the parameters of a particular model you're looking at. So what we can do in linear Boltzmann codes, we can use whatever phase space distribution these particles are produced at as the initial condition that we feed to Boltzmann codes, and then compute the evolution of structure in those cosmologies. So what's shown here is yet again my transfer function, my power spectrum normalized to CDM for three different production channels of sterile neutrinos. And what you can see here is something very similar that you've seen in the interacting dark matter cosmologies and also in warm dark matter cosmologies. You have this cutoff that occurs at the characteristic scale, below which you should not have any structure in the universe that features these candidates. Okay, so then we did what we do best, which is we took these predictions and we took again the census of Milky Way satellite galaxies and combined the implications for this cutoff in the matter distribution with what we know about the interactions, self-interactions of standard model neutrinos from just lab experiments, from collider experiments. And we were then able to exclude huge portions of the same parameter space. So in this case, to your point, there is a target region which we can go ahead and try to exclude. And in fact, if you require that the mediator is heavier, in particular heavier than a GeV, you can rule out this entire production mechanism. And this is only possible using the synergy of small scale structure with the laboratory experiments that probe the same physics. All right, so pausing again for any questions that people might have. Yes, George.
So you may have already said this, but I guess what is the reason to have sterile neutrinos if you have to have a mediator as well? Is it just that sterile neutrinos, right? Because in some sense, if you just want to add one thing, right, then you have to add phi and have the fourth neutrino.
Yeah, so you have to produce them in some way.
Yeah.
And introducing these standard model neutrino self-interactions is a mechanism to produce them. And that mechanism is motivated by mechanisms that people propose to explain the mass of standard model neutrinos. Okay. So I'm going to go into the details there, but this particular channel is something that people have talked about regardless of cosmology.
Right.
Yes.
You'd mentioned really briefly that you would use the same sort of machinery to look at warm dark matter as well. I was wondering if you could comment on those constraints at all.
Yeah, so warm dark matter bounds from the same observations are about 6.5 kV, which is competitive with most other bounds that we have.
Thanks.
Yeah, and in fact, we leverage them to put these bounds in a more rigorous way. All right, I want to talk about cosmological tensions for the rest of the time that I have. And I put a title of large scale structure, not to disturb you too much, but now here's my tension slide. For years I've refused to dabble into tensions, and then my students dragged me into it, and now I'm happy that he did, because it's really exciting in a lot of different ways. So cosmological tensions, in a nutshell, are the fact that data points from different probes that are supposed to measure the same quantity are mismatched, okay? So for Hubble tension, it's in words the statement that universal expansion that's inferred from the CMB is slower than that inferred from supernovae in the more local universe. And then the less prominent sigma 8 or SA tension is basically a statement that there's less clustering in matter that's measured directly by galaxy surveys at a particular characteristic length scale than what is anticipated given the anisotropies in the CMB. So in a sense, all of these probes are separated in scales and also in time. So it's really interesting to think about what causes these kinds of discrepancies in the data sets. So a full disclaimer, cosmological tensions absolutely could be systematics. I'm not the person to talk about systematics. I'm the physicist in the room, so I'm going to talk about crazy ideas to explain them, or maybe not so crazy. But I just want to acknowledge the point. This is how discoveries of new physics are also going to look like. We're going to see mismatches in our data and then explain them in models that work and that are predictive. All models that alleviate tensions, very important point, have additional free parameters. So all of the models that you're going to see me discussing today will have free parameters. Okay, so let me dive into it, and I keep pressing my phone just to check on the time. 15 minutes, something like that. Okay. All right, so I want to talk about the SA tension, the lesser one of the two, and especially in context of that same interacting dark matter that I was telling you about in context of satellites. Okay, so last year, this paper came out by Amon and Eustatio that basically made an argument that, okay, look, we can interpret the tensions possibly not as redshift dependence, the tension, specifically the SA tension, but could it be that the power spectrum, the linear matter power spectrum, deviates from lambda CDM in a scale-dependent manner? And so what they did is, instead of looking at a particular physical model, they tried to reconstruct the K dependence of P of K, and they came up with these particular shapes. Okay, notice the enormous uncertainty regions. Okay, so that's my disclaimer. But nonetheless, so when my students saw this, at that time, Adam Hick was working on folding together interacting dark matter codes with effective theory of large-scale structure codes. In other words, codes that allow us to go a little bit past linear cosmology and into a very slightly nonlinear regime, in the case of around of 0.2 or so, which a lot of the DESI and DS folks here are probably very familiar with. And Adam at that point was making so many of these plots that he pointed out in one of the group meetings that, you know, I've seen that shape before. In fact, if you make a portion of dark matter, not all of it, not 100%, but a portion interact with protons, scatter elastically, you end up with this long plateau, this particular characteristic K dependence. And so we decided to give it a shot. So this is very a posterior analysis, okay? So we saw the shape, and then we were like, okay, let's fix the fraction of dark matter to 15%, and let's see if it resolves the sigma 8 tension, okay? And so this is what we found. So in this analysis, I'll parse this plot really quickly. You have the interaction cross-section and S8 parameter that quantifies the amplitude of power on a particular fixed scale. And then different colors represent different models, and I'm dealing with CDM and IDM for interacting dark matter, and also different combinations of data. So if you analyze Planck under CDM, you end up with this black curve, whereas DES wants the same sigma 8 parameter to be in this gray band. That's the tension. Okay. Now, if I reanalyze Planck under interacting dark matter, I give it enough freedom to shift over to the left, better concordance with DES. But what was really interesting to me is when you add the BOSS data, so this is Lyman alpha and galaxy clustering, you actually end up shifting quite a bit to the left. And in doing so, you end up also shifting the posterior probability distribution on the interaction cross-section to the right and away from null, and towards some mild inconsistency with lambda CDR. Okay, so this is really, really mild. The delta chi squared here is minus 6.7. The only free parameter that we used is the interaction cross-section, but we did freeze the fraction of dark matter, which in principle should also be a free parameter in this analysis. Okay, so this is intriguing to me for a couple of reasons. One is that this is pretension physics. We didn't design this model. In fact, direct ejection has been searching for years. We're looking at lower masses, but the interaction structure is the same. It's consistent. It's consistent across the data. It's not like BOSS likes it, but DS doesn't, and so forth. All of the data sets kind of push in the same direction. Interestingly, it does not affect Hubble tension, which most of other solutions for sigma tension do mess up the Hubble tension. And the most interesting one to me is that it's imminently falsifiable. So I'm going to go back to this plot really quickly and argue that the level of suppression you see for 15 or maybe between 10 and 15% dark matter interacting, this amount of suppression is something that we can begin to probe by population of satellite galaxies that LSST will be able to probe. So this is a model we can falsify within the next. Okay, I'm nearing the end. Am I nearing the end of the time? Oh no, I have another 10 minutes.
Yeah.
Okay.
Yeah.
All right. How are you guys doing? Yeah. Okay. Students are nodding in the back. Okay. Awesome. So, are there questions on the sigma 8 story so far? Yes.
So it does seem to it clearly affects the S8 measurement. But if you add a small fraction of interacting dark matter, what happens to, let's say, the dark matter substructure at small scales, like
So at this
things like
point,
that?
this level of suppression is consistent with the Milky Way satellite population. We haven't done a direct analysis, but this is exactly where my statement is coming from, that it's imminently falsifiable. If we can push those bounds just a tiny little bit, we're going to put this model in tension with the data. In other words, if we discover a few more satellites, that puts pressure on this one.
And is there any physical motivation behind most of the dark matter being cold and not interacting, whereas a small fraction being interacting? Or is this
What does
highly?
standard model look like? What does standard model look like, right? It's a mixture of a lot of different phenomenologies, mostly in M, but a few different particles with different masses and so forth. So it's more of like, why not?
Okay.
Right? It's a step in complicating the model beyond all of dark matter being one particle with one mass and one free stream length and so forth.
I see.
Yeah. Yes.
So this analysis is with CDM plus some fraction of interacting dark matter and no baryons?
So no, there are definitely baryons.
I mean, like baryonic effects in your perspective.
Yeah. So in the modeling that we used, we're using the effective theory of large scale structure, which does include things like bias, baryonic effects, and so forth. Those are all marginalized over. Yeah, but that's a fair concern. Again. Yes.
Is there any way of understanding why it's the fraction of particle that interacts that matters versus the strength of the interaction?
Is there a relationship between the strength of the
Yeah.
interaction?
I mean, is that what the 15% meant?
Yeah.
It was that
Yeah.
number, right?
Yeah. Okay, so it's the fraction. That would be the fraction of dark matter that's interacting. So the level, so the onset of the cutoff, if you make all dark matter interact in the same way, the position of the cutoff in physical scale is a function of the interaction cross-section. If you decouple earlier, you move that cutoff towards smaller and smaller scales. The level of suppression here relates to the fraction that you make warm at early times through these interactions. So you control the shape. Okay, so perhaps an even more interesting story here would be one that relates to the Hubble tension. And in this case, I'm only going to deal with standard model neutrinos, but yet again, I'm going to consider their masses, but also self-interactions. So kind of like in that mechanism that I used to produce sterile neutrinos, but I'm not going to deal in sterile neutrinos for this bit of the story. Okay, so just a super brief review of the neutrino cosmology. So standard neutrino cosmology has neutrinos decoupling at around an MeV at the BBN scale. And then they're free streaming. They're basically a free streaming radiation component in our universe. And depending on the sum of their masses, they eventually start to cluster depending on what that number is, so when they become non-relativistic in the more recent history. So that's kind of the description of standard model neutrinos. So if you look at perturbations, and in this case, a very simplified, hopefully people have seen this visualization by Eisenstein and others. If you look at and you live in the DESI world, so I'm sure people have seen this. So here you see the Gaussian perturbation in the early universe, and what you see developing around it, this is your baryonic acoustic oscillation scale. So the size of that circle, you have a sound wave propagating through this universe. So in other words, this is the size of the sound horizon as well. If you look at what individual components of the universe are doing in this standard cosmology, I'm just going to wait for this Jeff to start from the beginning. If neutrinos are free streaming, the wavefront of neutrinos pulls a little bit ahead of the wavefront of photons and baryons. And it only has gravitational interaction, so it exerts a little bit of a tug of this wavefront, making, as a result, this BO scale ever so slightly larger than it should be in absence of free streaming radiation, in absence of neutrinos. Okay. So this is what happens in standard cosmology. Now, let's make neutrinos sticky, and let's give them a self-interaction, maybe described through this Lagrangian here, where you have some coupling constant, some new mediator particle. Let's make it heavy so as not to mess up with BBN and so forth. So you have a 4 fermion interaction, 2 neutrinos coming in, 2 coming out. And that kind of interaction is described by this effective Fermi constant, G effective here. So that captures the strength of the interaction and the interaction rate. Now, if you go from standard cosmology, which is supposed to be this solid black and red curve here, to a cosmology where neutrinos interact, I didn't say this is the temperature anisotropy power spectrum as measured by Planck. So if you go from standard cosmology, where neutrinos are free streaming since BBN, to a cosmology where they stay coupled until later times, what you end up doing is you boost power on basically all scales, very slightly, but more importantly, you shift the position of acoustic peaks towards smaller scales. Because remember, neutrinos rush ahead of baryons and photons and pull the baryonic acoustic oscillation to become a little bit larger. And in absence of that, because they're sticking together for a little bit longer, they will actually pile up in sync with photons and baryons, and that will lead to acoustic horizon scales that are a little bit smaller. So in other words, shifted towards the right in this diagram. And this is something we can measure in the CMB. In other words, it's something we can constrain in the CMB. So about 10 years ago, Surasin and Sigurdsson did the first analysis of Planck 2013 data. I will skip over my beautiful visuals, which I was really hoping to show you. And whoever wants to see them, I'll show them later. I love good visuals. Okay, so Sigurdsson and Surasin analyzed Planck data, and what they saw is the following. So this is the posterior probability distribution of that G effective self-coupling constant. Okay. And so this is something that we don't often see in cosmology. It's bimodal. Okay, it's consistent with lambda CDM, no self-coupling, early decoupling, and it's also consistent with an appreciable amount of self-interaction. Okay, so neutrinos, in other words, do not seem to have to be free streaming from early times. They could also be pretty strongly self-interacting. But if you do that to neutrinos, you have to pay the price and make the expansion of the universe a little bit faster to be in concordance with Planck data. What that means is that that self-interacting mode is shifted towards larger values of H naught. So this was very exciting as a potential, reconciliation of this Hubble tension. Okay, so this was status with CMB experiments act further, increase the significance of the second mode, and this rose a lot of interest amongst cosmologists in recent years. But self-interactions don't only affect the CMB, they also affect the matter power spectrum. So if you plot that same quantity that I was playing with this whole talk, and you do lambda CDM is going to be horizontal line, and then let's focus on the solid red here. This is some amount of interaction will actually produce a bump, an excess of power at a particular physical scale that corresponds to the size of the sound horizon at neutrino decoupling. So if you make that scale smaller, you push this bump to the right, you reduce the strength of the interactions, you decouple earlier. Okay, so this is a very, very interesting K-dependent structure in the matter power spectrum. So yet again, Adam turned the crank on analyzing all the large scale structure data that we had at that point in time together with Planck. So in Planck, newer measurements, you see that second probability mode. Well, once you add BOSS, Lyman alpha from EBOS, and then also DES, you end up actually completely erasing the probability in the lambda CDM. In other words, this particular combination of data, which is all the data for which we had the likelihoods that could predict clustering and wave cleansing of galaxies that we had the measurements for, all of these data combined prefer a decent amount of neutrino self-interaction and a delay in free streaming. Okay, so this is pretty honestly about a 5 sigma detection of G effective. Now here's why you should worry about this statement. So here I'm showing the delta chi-square breakdown as it comes from different pieces of data sets. Okay. And what I want you to notice is, okay, Planck is more or less ignorant, so everything here less than 1 sigma. BOSS and DES do push in the same direction towards the preference for this model over lambda CDM. But the vast majority of that push comes from Lyman alpha forest data. Okay. Single data set preference. And this is my last contentful slide, as I see you. But I will just say that the Hubble tension resolution is reduced in this particular model when all the data sets are added up. So that's an unfortunate feature, but still something that's very interesting to further explore. Okay, I will just say future outlook, I think looks great for searches for dark matter and other new physics with various probes, and even better modeling of satellite galaxies, like what people have already brought up in this talk, really understanding the substructure in these different dark matter scenarios. Not doing that linear theory order of magnitude thing, but actually modeling the substructure already can bring us down a few orders of magnitude deeper into this parameter space. But I think what's really, really exciting is to think about what are all the data points that we can put on this linear matter power spectrum through a variety of probes, because the K-dependence of how matter is clustered on a variety of scales really bears a lot of information that can help disentangle different effects that we may be looking for. I will leave you with my key points. Oops, sorry. I will leave you with my key points. And then if Elizabeth lets me, I will advertise a conference in a second. Will let me do that? Okay, I will do this. So there's going to be a conference and a workshop at KTP in Santa Barbara in early June. If you're not signed up to participate, the registration filled up uber quickly before we could even register all of our speakers. But it'll be, as I said to my group the other day, it will be free streamed on Zoom. So please join in and pitch into this community. And I'll just leave you with this picture. because it's just lovely. Yeah. No, I will do this, okay? Thank you.
Thank you, Vera.